Um, so hello to both of you. Welcome back to the Computer Theory tutorials. So yeah, today I'm gonna be covering a lot of the stuff that I wanted to cover last week. Apologies again for not being able to make it. Hello, hello. So the general topic that we're going to be discussing today will be undecidability, which is a very broad and very large topic, but for the purposes of the class, it's also really just going to be essentially discussing your problem set 5, basically. Um, so I'm going to give you some more like theoretical notes, just because I think they're kind of important and they might not have been presented like this in the lecture, and then we'll try to do some exercises related to that. So the first thing that I want to talk about is maybe just a reminder um, of some concepts that you've already seen, but just under slightly different names. So there are two very important concepts that have taken up most of your time in the last few weeks in Comp 30, which is the topics of Turing, recognizability, and decidability. In the lectures, these are typically referred to as recursively um, enumerable and as recursive. So these are classes or families of languages. But I think Turing recognizability and decidability are much more intuitive names, so I'll be sticking to those. And so just as a reminder slash a review, what is Turing recognizability and decidability? So let me give you two quick definitions. So for Turing recognizability, which I'll just write for as TR, so we say that a language is Turing recognizable. So TR just stands for Turing recognizable. If there exists a Turing machine M such that the Turing machine recognizes L. Okay, so this is very similar to the definitions you've been giving about regular languages and also about context-free languages when they were talked about in terms of PDAs. So the idea is that, L is Turing recognizable if I can build a Turing machine M, right, which recognizes every every element that belongs to the language and only every element that belongs to the language. So essentially, that means that I can build a Turing machine M, where if I have a string W in L, then the Turing machine always will tell you, yes, this string is in L, right? So it will always accept these strings. However, remember last time when we talked about Turing machines, there's sort of three possibilities when it comes to Turing machines and their inputs. Either they can say yes, so they can accept, or they can reject, or they can loop. And so when we talk about a language being Turing recognizable, the other thing that you have to keep in mind is that if the string is not in L, it's not guaranteed that the Turing machine will say no. The only guarantee that we have for the Turing machine is that it won't say yes. So either the Turing machine on an input string W, which is not an L, will say no, or it will loop. Okay, so those are the two possibilities. Hello, hello, hello. Okay, so this is just a reminder of the definition of Turing recognizability, which, like I said before, in class was sort of talked about as recursively enumerable. But I think Turing recognizability is a more intuitive definition. Then the other definition that I want to remind you of is of decidable languages, which I'll just abbreviate as DEC or DEC. So a language is decidable if there exists a Turing machine M which decides it. Okay, so which decides L. So what do we mean by L? We mean that L of M, there exists a Turing machine M such that L of M is equal to L, right? And for every input string in a sigma star, M either accepts or rejects W, right? So in other words, the Turing machine always makes a decision. It never loops forever on any input string, right? So if you want to, again, represent this pictorially, then we can just copy this machine here. And, we still have this guarantee. So we still have the guarantee that M recognizes L. But now we have the additional sort of restriction that for a string not in L, the Turing machine will always say no, right? So it's not either going to loop or say no, it's definitely going to say no if the language is decidable, right? And so the reason why decidable, I think, is more intuitive is because it tells you what the Turing machine is doing. It's always making a decision, right? So you can think of looping as just you're never coming to a decision. You keep thinking about a problem. Whereas, decidable means that you're always sort of at some point in finite time saying yes or no, is this string or that? Okay, so this is just a reminder in case some of you had sort of forgotten or you didn't quite know what these words were in the problem set, right? Yeah.
Context-free languages are subset of the recursive languages, right?
Yeah, very good. So let me draw the hierarchy because yes, regular and context-free languages are subsets, strict subsets of the decidable or recursive languages, yes. So if we look at the Chomsky hierarchy of languages, which I'll just write as sort of the language hierarchy, no need to mention Chomsky all the time. So what we've seen in sort of Compton 30 is we have several classes of languages. The simplest class of languages that we've seen are the class of regular languages. So those that can be recognized by DFAs. DFAs always halt, so that's why it's going to be a subset of decidable languages. Then slightly bigger than regular languages, we have the set of context-free languages, right? For context-free languages, we have the CYK algorithm, which always halts. So then we have an implementation of a machine that says yes or no given any string, right? And then outside the context-free languages, then we have the set of decidable languages, right? So decidable languages include, for instance, something like, AN, BN, CN, right? Something that we kind of designed a Turing machine similar to something like this in the previous tutorial. And most of the problems that you can think of, most of the languages that you can think of are in fact decidable. But there are some which are not decidable, but Turing recognizable. So that's why we have this being a sort of strict subset, right? So an example of a language which is undecidable. So there does not exist a Turing machine that always makes a decision for any input and accepts that language and only that language. So one example is the halting problem, which we'll talk about in a second, which I'll just write HP. All right. Another one which you've actually seen in the lecture is the universal language, so L sub U, right? I think you might have seen this a few lectures ago. So Jérôme called this the universal language. But in fact, there's actually a much more intuitive way of talking about the universal language, which is as a decision problem. So the universal language is actually sort of equivalent to the acceptance problem. And the acceptance problem asks, given a Turing machine M and an input string X, does M accept X, right? This is the acceptance problem. And the reason why it's equivalent to the universal language is because the definition of this guy was all of the encodings of Turing machines and inputs such that M accepts X. But then all I'm doing is I'm saying, you can take this sort of proposition and talk about it as a decision problem, right? So, you have an M and X and you just want to know, does it accept or not? If it is, then it's in this language. If it doesn't accept, then it's outside of this language. Okay. So that's the connection. And there's always a sort of one-to-one connection between a problem and the language corresponding to that problem. Okay, and beyond the universal language, another one that you've also seen, which wasn't even Turing recognizable, was the sort of language that you obtained from a diagonalization argument. So maybe you might have remembered this from the lecture. Diagonalization argument. So an argument sort of similar to Cantor's argument that the reals are uncountable was given to show that there exists a language that is not even Turing recognizable. And the reason why I bring this up is because to show that LU was an undecidable language, or to show that the acceptance problem was an undecidable problem, what was done in the lecture, in one of the previous lectures, was to give a reduction. So it was shown in class that the acceptance problem, which is what I'll be referring to from now on as the sort of universal language, was undecidable. And the way that this was shown was through a reduction, right? Which is going to be the first actual hands-on topic of this tutorial. So the way that you had shown that AP or L sub U was undecidable was by reducing it from the diagonalization or the sort of diagonalized language. And so reductions will be the first kind of major topic of today's tutorial because they'll be quite important for the problem sets and the final exam. Okay, so any questions? This was mainly just review of the lectures. So any questions about this? No, okay. Okay. So now what we want to do in the next, let's say, a half hour is to get a bit more comfortable with doing reductions because they're quite present in the problem sets and in the final exam. So let me just give you first the intuitive idea of what reductions are in case you're not taking 360 or maybe you've taken it a while ago and you're a bit rusty. So given two decision problems, so problems where the answer is yes or no, P and Q, a reduction, so P to Q, is so a reduction, let's write it like this. A reduction from P to Q, which is written P less than or equal to Q, is a method to show that the problem or the decision problem Q is, quote, at least as difficult as the decision problem P, right? So this is within quotes because it's a fairly intuitive high-level idea, right? But this is the general sort of thing that you're doing in reductions is you're given two problems and you want to show that one is harder or at least as difficult as another one, right? So how do you do this? Right. So the intuition as to how you do this is you want to show that if you could solve Q, then you could also solve P, right? So the example I usually like to give is, think of like two exams. So I have exam 1 and I have exam 2. right? Suppose that exam 2 has a subset of the questions from exam 1 plus some additional questions. So it's kind of intuitive that exam 2 is harder than exam 1. But how do you show this kind of using this intuition? Well, you just say, if I had the answer key for exam 2, then I could definitely solve exam 1 because all the problems or all the questions in exam 1 are contained in the answer key of exam 2, right? Plus some other stuff. So this is the general kind of idea of reduction is if I have the answer key for this, then I want to show that I can use it to solve this, right? This is the general process. And so then why do we do this? Like, how is it relevant to what I talked about at the very beginning, that is decidability and Turing recognizability? So we do this because if we've shown that P is P reduces to Q, right? So the other way that people sometimes say this is P reduces to Q, right? And we already know a priori that P is undecidable, which means that there does not exist a decider, a Turing machine, which decides P, then this is already proof or evidence that Q will also be undecidable, right? So this implies that Q is undecidable. Why does this imply this? Because if I've established a reduction, right, the reduction tells me that I can solve P by solving Q, right? So now suppose that Q was decidable, then I would have a decider, right? An algorithm to decide Q. But because I have a reduction, that means that I can also decide P, which is a contradiction because I know a priori that P is undecidable, right? The same logic holds for NP-complete or NP-hard reductions. So if I know that the problem on the left, if I know that the problem on the left is NP-hard, right? Then this implies that the problem on the right is also NP-hard. Why? Because if this wasn't NP-hard, if it was actually possible to solve it in sort of polynomial time with a deterministic Turing machine, then I could just use the solver for Q, right, to solve P in polynomial time, and therefore P would not be NP-hard unless P is equal to NP, right? Okay. So this is why this is important, because it's a technique to show that something is not decidable or not in P, right? Okay. Now this is a review of the logic of reductions. Yeah?
I think that P is like reduces to Q.
Yeah.
P is like in the language hierarchy you show that like P is like a subset of Q.
Yeah, kind of. It doesn't necessarily have to be. So the question is like, does this mean that P is sort of a subset in the sense of how problems can be a subset of Q? It's not always the case because it's possible that you have two problems. So in fact, the halting problem and the acceptance problem, there's a reduction, which we'll do in a second, from the acceptance problem to the halting problem, but they're in the same sort of class of problems or of languages. So it just guarantees that it's not in a hierarchy lower, right? Make sense? Okay. Good question. Any other questions? No. Okay. Maybe one last thing that I'll say before we look at a concrete example is I'm always going to use the same blueprint to do reductions, which is the following. So in a reduction, what I want to show is that I can solve P by solving Q, right? So what I want to do is I want to kind of create a Turing machine, which is going to be this box. And this box is supposed to be a P solver, right? So a solver for the problem P, right? What is the solver for the problem P going to do? It's going to take an instance of the problem P. So this is I sub P. It's an instance of the problem P. And if P is a correct solver that decides the problem, then it will say yes when the answer to the instance is no. It's yes. And no when the answer to the instance is no. Right? But now, how am I going to create the P solver? Well, I'm going to use the Q solver, right? So the Q solver is going to be within the box, right? And the Q solver itself returns yes, right? So this yes, this first yes should typically feed into the second yes, right? So I'm using the output of this solver as the output of this larger one. And the same thing for a no, right? But now the Q solver, right? The Q solver accepts instances of type Q, right? So the Q solver accepts instances of type Q, right? But what I have here are instances of type P. So what that means is then in the P solver, in addition to calling the Q solver, I also have to have what I will call an instance modifier. An instance modifier. And the goal of the instance modifier will be to convert instances of type P to instances of type Q, such that their answer is preserved when they're passed through the Q solver, right? This is what you want to do, okay? And the only restriction is whether this is kind of like an undecidability versus a NP hard reduction. If it's an undecidability reduction, so for undecidability reductions, the instance modifier, so IM, should be computable, which means everything that you do in the instance modifier should take finite time. It doesn't matter if it's exponential as long as it's finite, right? For NP-complete reductions, so for NP-complete reductions, the instance modifier should be polynomial in time. Okay. Why? Because if this is polynomial in time, and if this were polynomial in time, then the problem I'm trying to, then the reduction would show that I can solve problem P in polynomial time, right? Just because if you compose two polynomial time solvers, then you still have polynomial time. Okay. Well, I guess if you have, not necessarily if you compose, but if you have like an additive sort of thing, then it's polynomial. Okay. Okay, so this is the blueprint. Okay, so now let's try to make this a bit more concrete by looking at a first reduction where we want to show that the following decision problem is undecidable by reducing it from HP, or sorry, AP. So what we want to show is undecidable is the halting problem. Yes. Yes. NP complete. Turing machine M. So what is the halting problem? The halting problem asks a slightly simpler question than the acceptance problem. Is just given a Turing machine M and an input X, right? We want to know whether M halts on X. Right, so halting, that means that either it accepts or rejects X. Because in both cases, in both accepting and rejecting cases, the Turing machine halts. It only does not halt if it loops on the string forever, right? Okay, so how am I going to do this? Well, the question tells me that I'm supposed to do the reduction from AP to HP, right? So let's just copy the blueprint that I've created here and paste it here. And essentially now what I want to do is I want to create an HP or an AP solver. Question for you. Yeah. Right. An HP solver is yes. So I want to make an AP solver, right, from an HP solver, right? Because I want to show that this is at least as difficult as this. So to do this, what I want to say is, if I could solve this, then I could use this solver to solve this problem, right? So yeah, very good. Okay, so how am I going to do this? So now I have, an instance of the AP problem as the input. So that's a Turing machine M and an input X. And the instance of the HP problem, that's going to be another Turing machine M prime and some input Y, right? So in this case, the types of the inputs are the same. They're both a Turing machine and an input, but maybe I have to do some manipulation, right? So it might be a bit hard to sort of think of what to do in reductions. And so the tip that I would give is when you first start, just try to make the instance modifier as simple as possible and see if it works. And if it doesn't, see where it breaks, right? So the tip here is keep the instance modifier as simple as possible. Okay. So in this case, well, what's the simplest possible instance modification? It's, don't modify anything and just take MX and copy it as the instance of the HP solver, right? So that's going to be the simplest possible modification. Let's see if that works, right? So consider the input. The input to the AP is going to be the same as for now, right? Consider the following instance modification. Essentially, what the instance modifier does is it just copies the Turing machine and the input. So it says, M prime is going to be M, and Y is going to be X, right? So let's see if this works. So I have my Turing machine M and my input X, right, which is Y and M prime. So I essentially want to see, do yes answers get preserved as yes answers, and do no answers get preserved as no answers, right? So to do that, I have to do like the analysis. I have to check every possible case, right? So does this work? Right? So if M accepts X, right? So if I have from the input a yes answer, so M accepts X, then what happens? Well, M prime and Y are the same as M and X. And so then M prime also accepts Y, right? So M prime, I'll just say, because Y is X, I'll just keep saying X. So M prime accepts X, and therefore M prime halts, right? So that means that I took a yes answer here, so an answer where M accepts X, and then it remains a yes answer when it gets transformed into an instance of the halting problem, right? So then that's good, that works. What about if M loops on X, right? So if M loops on X, then because M prime is the exact same code as M, then M prime will also loop on X, right? So that means that M prime loops on X, right? And therefore M prime does not halt, right? So therefore M prime does not halt, right? And so what that means is, if I go back to, if I zoom out a little bit, if I have a no here, right? Where in this case the no is because I'm looping, then it remains a no, right? So far it seems that things are working, but of course I've saved the edge case for last, which is if M rejects X, then so does M prime, right? Therefore, that means that M prime halts on X, right? And so that means that here the answer to the answer to the acceptance problem was yes, and it remained yes here. Here it was no, The second problem was no. And it remained no here. But here we unfortunately have a mismatch, right? Which is that the answer here is no, right? M does not accept X. But for the halting problem, M prime halts on X, which means that the answer here is yes. Right? And so this is not a correct solver for the acceptance problem, right? Remember, I'm trying to create a solver for the acceptance problem. This doesn't work because in some cases where the true answer to the acceptance problem is no, the HP solver that I'm using as a subroutine is saying yes instead, right? So that's kind of a problem, right? So this doesn't work. So can someone try to propose a fix? Yeah. Yeah. Such that.
it loops back on C's like when it rejects.
Yeah. Yeah. Excellent. Very good. Very good. So excellent idea. Excellent idea. So yeah, come on. Okay. All right. So let's just write this breaks because when M rejects X, the HP solver says yes. And so the fix, right, is when M rejects X, make M prime loop on X, right? And it's very easy to make a Turing machine loop on an input. You just create an artificial infinite loop, right? It's very easy to do that in Python, just a while true continue. So you can just imagine it's just the Turing machine equivalent of that, right? So for instance, it could be something like this. So, I have X and I have my initial Turing machine M, which has an accept state. And now let's just suppose for simplicity that the Turing machine actually has a reject state. We didn't look at reject states in the tutorial for Turing machines, but suppose that it had one, which is essentially just like when the Turing machine doesn't know what to do, it's sort of in a jamming configuration, then it just goes to the reject state and then just says no, right? So what we do with this Turing machine M is we create a slightly larger Turing machine M prime, right? Where M prime is the same as M, except that when M reaches a reject state, then M prime keeps on going and goes to some looping state, right? So you can just imagine this as being like some self loop with all of the letters of the tape alphabet, right? And that's going to cause an artificial infinite loop to occur. Maybe a bit more compactly, which is a bit more compactly, because this is going to be the way I'm going to represent future reductions. The way that you could also write this is, M prime on input W, right? What M prime does is that it runs M on W. If M accepts W, then then M prime itself accepts the initial input. If instead M rejects W, then what M prime does is that it goes into an infinite loop. So then loop forever. Okay. So this is the slightly more compact way of representing this. And this is, of course, assuming that so the instance modification is, we have this as the M prime. So the instance modifier takes M and X and then returns M prime, but then the input is still X, right? So then why does this work? Just to conclude, so why does this work? Why does this mean that we actually have created an AP solver, right? Because M accepts X, right? So M accepts X if and only if this sort of line executes, right? And so this line executes if and only if M prime halts, right? Because otherwise M prime will not halt. Either it will be stuck in an infinite loop here, or it will be stuck in an infinite loop here, right? So I have if and only if M prime halts, right? And so M prime halts on X, right? What that means is that my HP solver, right? Remember, I'm using the HP solver. It's going to say yes in that case, right? And it's only going to say yes in that case. And that means that because the output to the output of the HP solver is being used as the output of the AP solver, then that means that the AP solver says yes when and only when M accepts X, right? So therefore, that means that I have a correct AP solver, right? So I've created, right, an AP solver from an HP solver, which therefore means that I have the reduction AP to HP. And so since AP is undecidable because it was shown in class, this implies that HP is undecidable. And maybe just to hammer this point home, why does this imply this, right? Because suppose HP was decidable, right? So suppose I actually had a decision procedure which worked in finite time that decided the HP problem. Then that means that if I go back here, this would work in finite time, right? This works in finite time. And I know that if I have a yes here, then this is going to be output as a yes in finite time. Otherwise, it's going to be output as a no in finite, right? So that means that I have a decision procedure that works in finite time for the AP solver, which is impossible because it's undecidable, right? So then I have a contradiction, and that means that HP is undecidable. Okay, does this make sense? I know it's a lot of words, but hopefully this is my best attempt at making reductions simpler. Good, okay. All right, let's look at another example, which I will give you some time to try. So in this case, we want to show that the all decision problem is undecidable. So what is the all decision problem? The all decision problem says if I'm given a Turing machine M, I want to know whether L of M is sigma star, right? So I want to know whether M accepts everything, right? And so intuitively, this is probably undecidable because the acceptance problem was undecidable, right? And all sounds like it's harder than AP because in all, you want to check whether the Turing machine accepts everything, right? So what I'll do is I'll let you try for a few minutes to come up with a reduction for AP to all. Okay. So I'll give you maybe three minutes. Hmm.
The way that everything is set up in that box where we have
Hmm.
a instance machine and so on,
Hmm.
we are basically expanding the instance such that it becomes
Modifying it. I wouldn't say expanding necessarily.
but the way we're putting it is that acceptance problem, for example, is smaller than the whole problem in a way that
Less difficult. Less difficult. Not smaller.
it's what?
Less difficult.
Less
Or at least as difficult.
Well, then how come you make it problem that is not difficult with all that's the modification, right?
I mean, you can definitely make a very simple, like there's always a reduction from an easy problem to a hard problem, right? Right. Like logically, if I can solve the hard problem, I can use the answer key to solve the easy problem. Right. But never the other, I mean, not the other way around is very suspicious, right?
Of course. Otherwise, we can solve the universal problem before running the practices.
Something like this. Yes, that's right.
Can you build the HQ solver using the HQ solver?
Yes, you can do the other way, actually. Yes, good point. Yes. Yeah. So yeah, so just a small aside, um, there's an observation that it does seem like you could also do HP reduces to AP, right? Which is true. You can do this. Um, so that actually means that in like theoretical CS, what we say is that these have the same sort of degree of difficulty. So if there's what I'm actually showing you here is a Turing reduction. And if there's a Turing reduction from AP to HP and from HP to AP, that means that they have the same sort of Turing degree. Is the general yeah. And then it's kind of cool because then you can manipulate degrees of impossibility, and then that's fun. Okay, so hopefully you've had a thought about this reduction. What do I kind of want to do here, right? So again, I want to create, in this case, an AP solver again, right? I want to create an AP solver from an all solver, right? So what does the AP solver take in? It takes a Turing machine M and an input X, right? For which I want to know if M accepts X. And, it should say yes if it does accept and no if it doesn't, right? But what I want to do to sort of solve or decide this problem is by using the all solver. So then that means that I need to create an instance modifier. So I'll just write IM such that the instance modifier outputs, in this case, the instance of the all problem is just a Turing machine, right? So there's no input, right? So that means that I just want to return, the instance modifier just wants to return M prime such that the all solver says yes, right? So the all solver says yes, if and only if M accepts X, and the all solver says no, if and only if M does not accept X, right? So the goal here, the goal is I want to design, right? So the instance modification wants to sort of design an M prime such that the language recognized by M prime is sigma star, if and only if M accepts X, right? Okay. And so what you have to remember when you're making the instance modifications is that they're kind of like a function which take as input M and X, right? And output M prime. But it's a bit weird because it's kind of like a second order function. It's something that, in this case, like intakes a Turing machine, which is itself a function, and outputs another Turing machine, which is also a function, right? So that's why it's kind of like a second order thing. But that means that the instance modification, or like if you think of the instance modification as an algorithm, it has access to M and X, right? So that's kind of a key thing when you're designing the sort of Turing machine M prime. So what is M prime going to look like? I'm going to sort of use the syntax that I introduced before. So M prime is going to take some input. Let's just call it W, right? And what the instance modifier is going to tell M prime to do, right? So the instance modifier is writing the code for M prime. And what it's going to tell M prime to do is the first thing is to essentially erase the input that it's given. So erase W, right? And instead load M and X, right? So it's going to load M and X onto its tape, right? And the reason why is because what I'm going to do is I'm going to use the code of M to run it on X, right? But to do that, I actually have to load the code, right? And I have to load the input. But remember, this is the instance modifier that's doing this. And so even though like in the input here, there doesn't look like there's an M or an X, it's the instance modifier that's kind of taking it and putting it here. Right? So just be aware of that to not sort of be duped. Then what the instance modifier is going to write in terms of the procedure for M prime is it's going to tell M prime to run M on X, right? Just as it normally would have without this other stuff, right? And then what M prime is going to say is it's going to say if M accepts X, which is something that sort of a Turing machine inspecting another Turing machine can do, right? It can do this because it just checks, oh, you got to an accept state, right? So if that happens, then the larger Turing machine, which received an input W, will accept W, right? So if that happens, then the Turing machine M prime will accept the initial input W. And it doesn't matter that M prime erased W, right? Because as long as M prime gets to an accept state, it doesn't matter what it did with the input. As long as it gets to an accept state when the input was at the very beginning on the input tape, that means that accepted W, right? So what does this mean, right? What does this mean if we analyze this a bit more? Let's look at the case where M accepts X. So if M accepts X, right, then what happens, M prime does all this stuff. It runs M on X, and eventually M accepts X. So then this if statement evaluates to true. And that means that M prime, no matter what the input W, will accept, right? So that means that no matter what the input W, M prime will accept it, right? Because why? Because the if statement, so the if statement on line 4 is always true. Okay. So what does that mean? What does it mean that I have a Turing machine which accepts no matter what? What is L of M prime? Sigma star. Yes, very good. Thank you. Okay, that means that it's sigma star. Excellent. So that means that I have a yes that goes to a yes, right? The all solver is going to look at this machine and it's only going to say yes if M accepts X. What if M does not accept X? If M does not accept X, then, either M loops on X, so then it gets stuck in an infinite loop here, or it rejects X, right? Which means that this doesn't evaluate M prime halts in a not an accept state, and so it rejects the input, right? So in either case, this means that M prime will not accept any input W, right? Either because it's stuck in an infinite loop of an infinite loop, or because it rejects, right? And so that means that L of M prime will be what? If I have a Turing machine, if it will not accept any string, yes? Yes, empty language, right? Right? Okay, so that means L of M prime is empty, right? And last time I checked, the empty set is never actually equal to sigma star, right? So that means that a no answer remains a no answer, right? So that tells me that the all solver that I created or that I assumed exists will output yes if and only if M accepts X, right? So that means that, this says yes if and only if the initial input here was yes. If it's no, then it returns no. So that means that I have an AP solver, right? So that implies that M accepts X. So therefore, I've created an AP solver using an all solver, right? Which implies that I do have that AP reduces to all. And since AP is undecidable, this implies it's exactly that all is also undecidable. Again, just to give me a second, just to hammer this point home, why does this imply this? Because suppose all was decidable, right? Then that means that this solver actually exists and works in finite time for any input, which means that I can do this modification, which is finite, and take an mx and convert it to an m prime and always decide in finite time whether m accepts x, which I know is impossible because the acceptance problem is undecidable, right? Nice. Any questions? Yeah, you had a question?
What language Turing machine and prime is equal to empty set?
That just means that the Turing machine m prime that I created here on any input w, it never accepts, right? It either loops or it rejects. So it's kind of like saying the language accepted by the DFA is empty. It's the same idea. Make sense? Okay. Yeah, other question? Yes, you need an if and only. Yes. You need a yes goes to a yes and a no goes to a no. Yeah. Yeah.
Say that you were saying something like if the acceptance problem is undecidable, then so is the universe, nothing, all.
If the all problem is decidable, then the AP problem is decidable, right? Why? Because if the all problem is decidable, by the definition I gave, maybe 40 minutes ago, that means that this Turing machine M exists and always makes a decision in finite time, right? So this thing exists, this gadget exists, right? And I know the instance modification works in finite time. It's a computable thing, right? So that means that I have something that takes finite time and some other thing that takes finite time, which always correctly says yes or no, given an input of the acceptance problem. So that means that I've created a decision procedure, a Turing machine that decides the acceptance problem. Okay. Nice. Good. Okay, cool. Excellent. So now let's take a small break from reductions and discuss another very important topic for the final and the problem set, which is Rice's theorem. And so the motivation for Rice's theorem is that reductions, as we've talked about them, are kind of hard in the sense of they're difficult to do, right? And so Rice's theorem is there as kind of a way to, as an easier way to show that a decision problem is undecidable. So you can't always use Rice's theorem as a replacement for reductions, but you often can, which saves you a lot of headache and arguments, right? And to be able to talk about Rice's theorem, I need to define the notion of a property or properties of languages. Because the key idea of Rice's theorem is that a decision problem, which talks about a property of a language, is always undecidable, right? So if you can show that a decision problem is actually talking about a property of a language, then by Rice's theorem, you can immediately say it's undecidable and skip the reductions, which is kind of nice. So what do we mean by a property of a language? Suppose I have a non-empty alphabet, and I have the space of all possible languages. So this is the power set of sigma star, right? So each of the individual points here are languages, right? So here L1 is a subset of sigma star. Then a property of a language is a partition of the power set of sigma star, right? So for instance, L is equal to sigma star, right? This is a property of a language because it might partition this set like this. Whoopsie, yeah, sure, like this, right? Where this is the part of the set of languages that satisfies the property, and this is the part that doesn't, right? So there's a binary partition, right? So another example of a property of a language is maybe the cardinality of the language is greater or equal to 330, right? So this is another property of a language because if you imagine, you have a bunch of languages, right? Some of them have cardinality less than 330, so maybe they're on the right of the purple line, and some have cardinality greater or equal to 330, so they're on the left. So that's another partition of the power set of sigma star. Maybe one last one is oopsies, 0, 1, 0 in L, right? This is another property of a language, right? Because there's languages that contain 0, 1, 0, 1, 0, and maybe they're under this green line, and then there are languages that do not contain 0, 1, 0. So they're above this green line, right? So a property of a language is something that partitions this space. And so then Rice's theorem, what Rice's theorem says is whenever you have a decision problem about a non-trivial property of a language, I'll define non-trivial in a second. That decision problem, so DP is for decision problem, is undecidable. So property of a language, right? This is what we've just talked about. Non-trivial, what does this mean? Well, a property, I'll just define the actual positive statement. A property is trivial, right? If it's always true or it's always false. Right, so a property is non-trivial when you have the negation of this, right? So there exists at least one language where the property is true and at least one language where the property is false, right? Okay, so this is Rice's theorem as a reminder. Now, how do we use it? Okay, that's going to be the next thing we'll talk about. So using Rice's theorem to show that a decision problem is undecidable. Okay, so let's just look at examples. I have more theory, but I think it's more illustrative if we just immediately look at an example. So let's look at example 1, right? what I'm trying to do in all of these examples is to determine whether I can use Rice's theorem to show that it's an undecidable decision problem, right? So let's look at example 1, which will have decision problem 1. Decision problem 1 says, given a Turing machine, M, is the cardinality of the language accepted by M greater or equal to 0, right? And so to be able to know whether I can use Rice's theorem to show that this language is undecidable, I need to show two things, right? To use Rice's theorem, I need to show, so NTS is need to show, one, that the property of the decision problem, so of DP1 in this case, is non-trivial, right? So it's not always true or it's not always false. And I want to show that it's actually a property of a language. Okay, so let's start with this first one, right? Can I show that the property of this decision problem is non-trivial? No, right? Why? Because given any Turing machine M, the language accepted by M will have a cardinality of at least 0, right? You can't have a cardinality of -1, right? That makes sense. It's like I take away a string from you. No, doesn't make sense, right? So that actually means that this property is trivially true, right? So if I look at 1, for every language which is a subset of sigma star, I know that the cardinality of L is always greater or equal to 0. Therefore, the property of decision problem 1 is trivially true, right? In fact, so that actually means that this decision problem is decidable, right? I can create a decision procedure that decides it. I just create a Turing machine that always says yes, right? And so no matter what the input here, I should always say yes, which is what I can design a Turing machine, very simple Turing machine for, right? Something like, in fact, it's decidable. Here's a Turing machine that decides it. So let's create M prime, which on input X accepts X. Right, so this Turing machine M prime, right? M prime decides decision problem 1. Okay. So in this case, I cannot use Rice's theorem because actually the problem was not undecidable to begin with. Right, so this is one example. Right, is this clear? Yeah, okay, nice. Let's look at a second example where I have now decision property 2. So in decision property 2, or decision problem 2, sorry, which is going to talk about a property. I'm again given an input, which is a Turing machine. And now the question in decision problem 2 is, does M halt on every input string? Okay, right, so this is decision problem 2. Now I want to see if I can use Rice's theorem to show that it's undecidable. So the first thing I need to check is, is it non-trivial? In this case, yes, it's going to be non-trivial, right? I can define two Turing machines, one where the answer to the decision problem is yes, and another one where the answer to the decision problem is no. For instance, I can define M1, which on input X accepts X, right? And so this is a yes instance because given any input string, right, M1 is going to take that input string and immediately halt and accept, right? So here, this satisfies the property of decision problem 2, but just as a shorthand, I'll just write DP2 to overload notation. So I have a yes instance. I can also create a no instance, right? I can create the machine M2, which on input X loops on X, right? So no matter what the input, right, my Turing machine or my function always loops, right? It always just immediately throws into an infinite loop, right? So that means that, given any inputs to the Turing machine, it does not halt. In fact, it always loops. So then it's not true that it halts for every input string. In fact, it doesn't halt for any input string. So it's an even stronger negation, because here I just needed one string to loop on the machine. Now I'm just looping on all strings. I said that in a different way, but hopefully you get what I mean. So that means that this Turing machine does not satisfy. Does not satisfy decision problem 2. So it's a non-trivial property, right? So I have the first half of using Rice's theorem. Now I need to show the second half, which is I need to show that it's a property of a language. And so remember how I defined properties of languages. I said, you have the set of all languages, right? And then a property of a language is a partition, right? And so saying that it's a non-trivial property, that just means that, this guy contains at least one language, and this guy contains at least one language, right? So that was the point of saying it's non-trivial. But you might notice something weird, right? Which is I want to show that this problem is talking about a property, which is actually of languages, but it's always given an input that's a Turing machine, right? It's not given an input that's a language, right? So this is a bit weird, right? How do I show that it's actually a property of a language? Essentially, the way that I want to do that is I want to just say that the exact details of the Turing machine don't matter as long as it's talking about the same language. The property is always either satisfied or is always not satisfied, right? So a property of a language when we're given a decision problem about Turing machines is one where, I might have a bunch of Turing machines, right, which are all recognizing the same language L, and where the property of the property which seems to be talking about Turing machines is always being evaluated to true for all of these Turing machines. So that means that it doesn't matter which representative of L you pick, the property is always true, which means that really it's a property of a language, right? Because it's like, what do all of these machines have in common? The language, right? They're all accepting the same language. So that would mean that the property evaluates to true for the language, right? Similarly, you could have the other case, right, where you have these Turing machines, which are pointing to the same language, right? But now all of the Turing machines, when you ask the question about this property, it's always false, right? It's always not satisfied. So that again means that it's really not a property of a Turing machine, but it's a property of a language. Because again, this means that it doesn't matter which representative of L you pick, it's always the evaluation of the property is always going to be the same, it's going to be false. So that means really it's a property of a language which happens to be false in this case. So what you want to avoid, right? What you want to avoid is, you have a language L, and you have different implementations of L, right? Where, for instance, here the property evaluates to true, but here it evaluates to false, right? Because that means that it's not really a property of the language, it's a property specific to the Turing machine, to the implementation itself, okay? So formally, right, the way that this is written in like propositional logic, to check that a property of a Turing machine is actually of a language, I have to do the following. I have to show that for any pair of Turing machines, such that the Turing machines accept the same language. M1 satisfies the property. If and only if M2 satisfies the property. Let's just do this, right? So the property, let's say P. So I'll write this as something like P is a property of a language if the following holds, right? But this is sort of like the propositional way of talking intuitively about how I talked about the property here. Okay. Okay, so that was an important aside because it tells me now what I'm supposed to do, right? I'm supposed to check whether this statement is true, in this case for this decision problem 2. So this decision problem 2 is, given a Turing machine M, does M halt on every input string? Well, it turns out that in this case, this is a property which is actually implementation specific, right? So why do I say this? Because let's consider the language which is the empty set. I'm going to create 2 Turing machines that both recognize the empty set, but where one satisfies the property and where the other does not, right? So let's define M1, which on input X, what it does is it rejects X, right? So it just returns false, right? So in this case, right, for every input that's given to M1, M1 halts on that input, right? So that means that M1 satisfies the property of decision problem 2, right? But I can create a similar Turing machine, right, which accepts the same exact language, but where the property is not satisfied. Does anyone have an idea what the Turing machine should be? So it should accept the empty language, but it should not satisfy the property. Remember, the property is that it halts on every input. So what is the Turing machine that, yep. What is a Turing machine that does not halt on any input? Does work? No, concretely. Like, how would you write a piece of code that does not halt on anything? Yeah. Right. So M2 is going to loop on X for any input X. Then what is the language accepted by M2? Well, the language accepted by M2 is all the strings that reach an accept state, but no string reaches an accept state, right? The Turing machine is always just looping forever. So L of M2, so here L of M1 is empty, and here L of M2 is also empty. But in this case, right, M2 does not satisfy the property because the property was you halt on every input, right? So M2 does not satisfy the property of decision problem 2, right? And so therefore, that means that this is not a property of a language, so I cannot use Rice's theorem to show that it's undecidable. Even though actually in this case, this decision problem is in fact undecidable, you would have to give a reduction, which I won't do for time and sanity. Okay, nice. Make sense? Okay, let's do one last one because so far it's all been like negative cases. Maybe it would be nice to have a positive one. So let's consider decision problem 3. which is actually just going to be the all problem. So given a Turing machine M, is L of M equal to sigma star, right? So I want to determine whether I can use Rice's theorem to show that this decision problem is undecidable. Even though we're running short on time, let me just give you a minute to think about it.
No, I don't.
Let's just take it we say the language is the language is
Yes, but when you say language is the first,
right.
so that means also.
This Turing machine is
Oh, I was thinking I said the Turing machine.
no. All right. So hopefully you thought about it a little bit. Let's see if we can use Rice's theorem to show that this guy is undecidable. So remember what we need to do. We need to show firstly that it's a non-trivial property. Right. In other words, that we can find two Turing machines, one where the answer is yes and one where the answer is no, right? So hopefully that's not too difficult to see. I can define one Turing machine M1 that satisfies the property. Essentially what it does is it just accepts everything. So here L of M1 is sigma star. On the other hand, I can define a Turing machine M2 that does not satisfy the property. It can just be the one that rejects everything. So L of M2 is the empty set, which is definitely not sigma star, right? Nice. So it's non-trivial. Now let's see, is it a property of languages? Well, to show that, I need to show that this statement holds, right? So to show that this statement holds, it's a for all. So let me just pick two arbitrary Turing machines, M1 and M2, such that they accept the same language, right? So let M2 be two arbitrary Turing machines such that L of M1 is equal to L of M2, right? What I need to show now is that M1 satisfies the M1 satisfies the property if and only if M2 satisfies the property. So suppose M1 satisfies the property of decision problem 3, right? What does that mean? That means that L of M1 is equal to what? Sigma star, thank you, right? Because L of M1 is equal to L of M2, that means that L of M2 is also equal to sigma star, thank you very much, which means that M2 also satisfies the property of decision problem 3. Now, this is only one direction, but the argument is exactly the same in the other way, right? So that means that I have an if and only if, right? Which means that I've satisfied the condition for a property which seems to be of Turing machines to actually be of languages, right? So therefore, um, decision problem 3 is a decision problem about a non-trivial property of a language. And so therefore by Rice's theorem, the decision problem 3 is undecidable. Nice. So this was the other way, we gave a reduction, but we could have also done this. And that's it for this tutorial. We're technically out of tutorial sessions, but I'll give another extra one for NP-complete reductions, date TBD, and then I will also probably give a final exam review session, also date TBD. Great, thanks a lot. Have a nice weekend.